So we had been looking at color systems, is that correct? And we had been through the HSB system, where you have the hue, which is where something would fit on sort of the rainbow scale. The saturation is the purity of the color, and the brightness is how bright it is. And that's probably the most natural way to think about color. We saw the RGB system that computer systems use, where you have a red value, a green value, and a blue value, and those three things together tell you what the color is. And that's used by computer systems, but it's not as intuitive as the HSB system. And then we also looked at the LAB system, did we not? And that wasn't terribly intuitive at all. It was very hard to get a handle on the color components of the LAB system. And the main value of that was that you could separate out the luminance component from the chrominance component. So we have the lightness here. The lightness information is separate from the color information. And we saw that JPEG does some subsampling. I showed you this, did I not? And the point here was that when you subsample the color information, when you subsample the chrominance, it's not so bad. On the right here, there's 1/16 of the color information. 15/16 of it have been removed. When you do the same with the luminance, though, you really notice it. So the point here is that humans are much more sensitive to luminance than they are to chrominance. And so you can really get away with cheating on the color, and everything will look okay. So HSB, RGB, and LAB. And then the last one we're going to look at is CMYK. And this is the color system used in the printing industry. So with CMYK, you have cyan, magenta, yellow, and black inks on white paper. Now, if I'm not mistaken, mathematically, in a kind of a mathematically perfect world, I think just cyan and magenta and yellow all together would make black. But as it turns out, we use the 4 inks anyway because, well, first of all, black is way cheap. So it's the cheapest way to do it. So we have blue ink, purple ink, yellow ink, and black ink. Cyan, magenta, yellow, and K for black. So it's a subtractive system, so the more you add, the darker it gets. So unlike the RGB system, where the more light you add, the brighter it gets, with CMYK, the more ink you add to the page, the darker it's going to get. Okay? If you have no ink at all, well, there we have cyan 0, yellow 0, magenta 0, and black 0. If there's no ink on the white page, well, it's white. If you have no color ink and you have 100% black ink, well, it's black. Here we have 50% cyan and 50% yellow, no magenta and no black. That would give you green. So it's a little bit more intuitive, I think, than the RGB system because we colored with paints when we were kids. And so we know that if you mix blue with yellow, you get a kind of a green. That's something we have a better handle on. Okay? So cyan, magenta, yellow, and black. These colors look familiar? When you go to buy ink for your printer, these are the colors the ink comes in. Although mine actually has my printer was a 6 different colored inks. It was supposed to do super great things. So very often, well, usually the color ink packet and the black ink packet are sold separately because you're inclined to use much more of the black than you are the colors. Sometimes you can get the cyan, magenta, and the yellow individually, or you buy them as a pack. So if we look here at the top left, that blue there is 100% cyan, And so it's that shade of blue. 100% magenta is that color there, 100% yellow, 100% black. All fairly obvious there. You 36% cyan here and 42% yellow, that's a shade of green. Again, mixing blue and yellow to give you green is something we're familiar with. This one here is 54% black, so we have an intermediate shade of grey. That magenta and yellow there gives us red. I would have expected that actually to be much more orangey. With that much yellow in it, I would have thought it would have been very orange, but it turns out to be that red there. This yellow here is quite pale. It's not full yellow, it's only 66% yellow. So you can imagine there's just a little bit of yellow ink on the page. If it was a lower value, it would get even paler again. So like this blue here is 20% cyan, 19% magenta, and 8% black. You can see that it's paler than some of the others. This 30% magenta, 28% yellow gives us that pink there. So it's kind of more intuitive than some of the other systems. But of course, it's only useful if you're printing. If you're putting colored ink onto white paper. There are equations you can use to convert from, so if you have a shade of red, you might be able to say, well, that is, it's this RGB value. What's the equivalent CMYK value? So if you take CIT red, for example, which I think is very close to pink, if you take the red and the CIT logo, and you can see here, this red here, that, see, it's shocking, isn't it? It makes you fall off your seat. It's so close to pink. So if you take the CIT style guidelines, for example, it specifies the RGB value that you should use for your web pages and for your stuff on screen. And if you're printing something, it specifies the CMYK values for that color. In general, there is a lot of technology built around color specification and color precision. If you imagine you're working for Zara or something, and you're making a colored dress, and the top part is made in India, and actually being Zara, it's probably made in Portugal, and the bottom part is made in Morocco or something, and you specified a particular shade of pink. Well, when you bring them back to the factory and you want to put the top and bottom together, well, you want to make sure they're the same feckin' pink, So specifying color precisely is very important, and there's some amazing tools for that. There's also issues with different displays. If I was to call up these slides and show them on this screen, show you my screen, and let you see this screen up here, they wouldn't all be the same. One might be slightly bluer or yellower or greener or whatever than the other. So if you're working in the color business, then you need to calibrate your screen so that when you choose a particular set of colors to do something, someone else looking at them on a different screen will see the exact same colors. So I noticed it a lot going from, we noticed it last week, didn't we, where the colors weren't working on the screen properly? Was that you guys? No? I notice it a lot when I go from room to room. Sometimes the projectors don't work quite properly. And when you have black text on a white background, it's not so bad. When you're talking about different colors, it can actually be a big deal if the red part in the projector isn't working properly. So imagine if that was the only display you had. You might be turning up the red an awful lot so that it looks right. And then when someone looks at it on a screen where the red was working perfectly fine, there's way too much red. So you have these color calibration technologies where sometimes you can get something that clamps onto your screen and it adjusts so that everyone is talking about the same red and the same blue. This company here, AGT7, I don't know what they do, but they're in the color measurement business. And so this was an ad that I thought was quite clever. This is in a magazine for graphic designers and print designers, and of course they would all know that C0, M0, Y0, K100 is of course black. But the point being, you know, sometimes black isn't enough. You need to specify exactly what you mean. Similarly here, you know, you don't phone up India and say, you know, I need 500,000 orange skirts. Well, you know, orange isn't specific enough. So there are whole industries built around, but there's a whole industry built around color specification. There's even cool yolks you can get. Let's say you are, I don't know, you're working for Zara and you're on holidays in Italy and you see someone has painted a wall a really nice kind of orange. You might decide, oh my God, that orange is the next black. Like, you know, I must have it. Well, rather than take a picture, you probably whip out this yolk that you never leave the house without, and you can hold it up to the color, press a button, and it would tell you exactly what color that is you're looking at. It would give you the CMYK values. There's also a company, Pantone, you may have heard of them, and they produce these color cards. So in actual fact, if you were phoning up your factory in Morocco to order 5,000 orange t-shirts, you probably wouldn't specify the CMYK value. You would probably say, I want those to be in Pantone Orange 27. And at their end, they would have, they would know how to make Pantone Orange 27. You need this much of this and this much of this and this much of this. And when the stuff comes off the production line, they could get their Pantone swatch and see that it, you know, is matching perfectly. So there's a whole business of color specification for industries where color matters. Here's another example here. Little cyan 5, magenta 90, yellow 100, black 0. And we know that to be red, obviously. And the joke here is that, you know, for some people red is enough, but for professionals, you know, you need precision. And we sell you the stuff that lets you be precise. Now, this is all leading up to us understanding how images are coded and how images are represented in different formats and the features of different formats so that we can choose the best one for our needs. So in general, on the web, there are 3 image formats that would be considered standard. There's GIF, JPEG, and PNG. And each of those has different properties. There's some things some can do, others can't do. And so depending on what it is you're trying to do, one of these may be the best choice. And so investigating those choices is what your assignment 2 is all about. And that's what you're using Photoshop for. So we're going to start having a look now at images and how they're stored. Okay. So we're interested in compression and how that works and what that is. So compression is a reversible conversion of data to a format that requires fewer bits. And we usually do that so that we can store or transmit the data more efficiently. So imagine, if you will, that the post office charged you for letters not by weight, but just by the size of the envelope. So if I went to the post office with an A4 envelope and I was going to send it, I don't know, to South Africa or someplace, they said, okay, that's going to cost you €18 for something that size. Well, I might go, okay, look, I'll fold it in half. Okay, now it's only half the size, so now it's only going to cost me €8. Or I could fold it in half again, down to €4. Now we're down to €2. And now we're down to this tiny, tiny envelope here, which might only be €1 to send. So compression is a bit like folding up the letter so that it takes up less space. And of course, one of the problems is that in the compressed form, it's not a whole lot of use. I can't do a whole lot with this letter. I certainly can't read it. So when it gets to South Africa, the person would have to open the envelope and then unfold it. So that's like decompression. To get it back to the state it was in before I compressed it so that they can read it. And so now it can be read again. Now, we typically talk about two kinds of compression: lossy compression and lossless compression. So, if you compress something, transport it, and then decompress it, and the decompressed version is an exact replica of the original, then the compression is lossless. So nothing has changed. You haven't lost anything. Very often with images, though, we're prepared to accept some degree of loss in order to save money, to save space. But it can depend on the context. So if you went into Waterstones to buy a book, I don't know, say you're going to buy the last Harry Potter book, and it's €25. And next to them there are these like cheaper Harry Potter books, the same novel, same last one, and that's only €10. And you ask, why is that €10? Oh, well, it's the same book, but every 10th word is random. Well, like a book in which every 10th word is random is just not acceptable. You know, when it comes to text compression, there's no amount of loss is acceptable. It must be lossless. Now, I mean, if you had pictures of you on your holidays in the pub and you wanted to post them to your Facebook page, and it was going to cost you 80 cents to send a perfectly lossless version, or for 10 cents you could send one that was really, really good, but the color of the cocktails was a bit off. The cocktails looked a bit orange instead of red. You might say, screw the cocktails, you know, I'm going to send the 10-cent one instead of 80 cents. In most cases, we're talking about storing images, but of course on the web we're transmitting them across a channel, and there's a cost associated with that. So with images, we're often prepared to accept some loss, but I mean, if you went to the hospital and they did a scan of your brain, and there was an expert in Sydney who could detect, you know, whether you had a particular kind of cancer or not, and the hospital said to you, well, you know, this is a huge file now, and it could cost us €40 to transmit this file to Sydney. Or we could do it cheaper, and you could do it for €4, but it might be a bit blurry. You know, if it's of a life and death situation, well, you're going to say, you know, take my money, you know, send it twice, here's €80. So depending on the context, some degree of loss may or may not acceptable. I mean, if this was a wedding photo and I did this to it, you know, and went home and told my wife, I saved us loads of money on postage by folding up the wedding pictures and putting them in a tiny envelope, I'd be shot. So depending on the context, some degree of loss may or may not be acceptable. And that's what you're doing in assignment 2. You're investigating the relationship between the cost and the quality. So you're adjusting the quality and you're seeing how that affects the size, and you're evaluating the cost-quality trade-off. We saw, for example, in the labs that the JPEGs, when they were saved at quality setting 100, were perfect. We saw that when we saved quality setting at 80, they looked exactly the same, but were half the size. So that suggests that the quality setting 100 is very bad value, because you're paying twice as much, but you can't even see the difference. So what are you paying for? So there's very often a sweet spot where the quality is still really good and you get a good price. If you go higher quality, you're just paying for more but not getting more. And if you go lower quality, it just starts to look crap. And if you're selling stuff online, for example, you want it to look good. You don't want to use crappy images just to save a few cents. So the cost quality trade-off is an interesting one, and it's a trade-off you need to understand if you're saving images to be used on the web. This was a much bigger deal in the past when bandwidth was constrained. These days people are very fláthúlach with their bandwidth, and they're like, sure, whatever, it's free. But you can, if someone is in a constrained environment, if they're looking at stuff on their mobile phone, it might slow them down. They might decide, this is too slow, I'm moving on, and you've lost a deal there. Now, so I like to think of the techniques we use in compression as kind of like recycling. And when you talk about recycling, people say, no, it's not about the recycling. The first thing you must do is reduce the amount of stuff you're producing. Reduce the amount of waste you're producing. The next thing you need to do is you need to reuse as much of the stuff as you can. And only then, when you've done your reduction, done your reuse, can you think about the recycling. And actually, when it comes to images, we can do an awful lot in terms of reducing the amount of data that we're trying to send. And we'll see when we go look at video compression and how that works. They're actually going to do an awful lot of reusing as well as reducing. So first thing I'm going to look at is how you reduce the amount of data that you have. So in an audio file, for example, we would have a number of samples. So when you're digitizing something, every so often you look at the analog value, you record it, and you assign it to one of these quantization levels. Now that every so often can vary. So in an image, you might be looking at, doing that 300 times in an inch or 800 times in an inch. In an audio file, you might be looking at doing that 44,000 times per second or 22,000 times a second. But once you have your samples, once you have the data in digital form, you might decide, okay, that's taking up too much space, I'm going to subsample it. And subsampling is a posh term for just throwing stuff away. So you might decide, right, getting rid of half of it. Now actually, as it turns out, you might decide to get rid of a third of it, and you have to do some maths to sort of fill in the gaps. But at its simplest, you're throwing away every second sample. We can do the same for images. Let's say this here is a portion of an image, and these are the pixels. We could throw away every second row and every second column, which would leave us with 25% of the information that was there before. So there's only 25% of the information now. So instead of sending all of the pixels from Cork to Sydney, I might only send a quarter of them. I do every second one, skip a row, and then every second one there. And so that's a fairly brutal compression technique, but you do save a lot of data. The question then, what happens when that's received at the other end? If you've removed a lot of the data and it's time to decompress the image, how does that look? Well, there are two strategies really you can employ. You could increase the size of the pixels so that the image takes up the same space as it did before, and you just have bigger pixels. Or alternatively, you could try and fake the missing pixels. You could do some interpolation, it's called. So this is what the the larger pixels might look like. So we have our subsampled image. Here we just basically double the size, the width and the height of every pixel. So now we've got big chunky pixels. The image is the same size. Interpolation is a bit more sophisticated. You could imagine that if we see that this pixel here is light blue and this pixel here is dark blue, well, we could speculate that the missing pixel would have been an in-between blue. Here, this pixel is dark blue, and here this pixel is dark green. Well, we could speculate that this pixel here, then the missing one, might be a dark greeny blue. This might be a light grey, a light bluish grey in here. And so when we fill in the missing pixels, we might get something like that. So it's another alternative. But that causes the image to appear a bit blurred. But certainly you can throw away information and then try and fake it at the other end. Here, I have reduced the amount of data in the image considerably, and so we've got very, very big pixels then. If I'm not mistaken, this man is guarding the Portuguese Parliament. So the pixels are very, very big. Alternatively, we could do interpolation, so we don't see the blocky pixels, we don't see the chunky pixels. We just have a guess at what the missing pixels might have been. Now, in both of these examples, it's not every second row and every second column that I've thrown away. It's way, way more, just to emphasize the point here. And so when you do interpolation, you end up with it appearing blurry. So your choice is big chunky pixels or blurriness. Although, as we'll see when we come to look at image formats, it's more sophisticated than this. We can actually be more sophisticated in what we throw away. So the RGB system uses a byte for each channel. So it's 1 byte for the red, 1 byte for the green, and 1 byte for the blue, which gives you 24 bits. So you used to see people boasting 24-bit color. Back when mobile phone displays weren't great, they might boast about how many colors they had. Now we accept 24-bit color as just the norm. So that gives you the possible 16 million and odd colors. Okay. Now, here we were talking about reducing the sample rate, reducing the number of samples per unit of space. But of course, we can also reduce the size of the data by reducing the pixel depth, by reducing the number of bits used for each pixel. So instead of using 24 bits per pixel, we could use fewer bits per pixel, and then we would be able to save some space. But of course, that would give us fewer colors. And so this begs the question then, how many colors can you get away with? And if you had a photograph of me, I'm not wearing any orange today. So whatever bits in that color space were being used to represent orange, you could do without. So in general, it may be possible to get by with fewer than 16 million. Maybe 6 million is enough. As we'll see, you can actually get by with a lot less. So let's imagine, although this is obviously a very contrived example, that this image here is using 24 bits per pixel. So this image here is stored as RGB. And let's say I was going to reduce that to just 4 colors. Well, what would happen, and actually there's an interesting optical effect here, more so on my screen than yours. There's 4 colors on this screen. It appears actually there's a bit of an optical illusion there where there's like a gradient or something, but there's not. So this image has 4 possible colors. So every pixel in this image is one of 4 colors. And what you have to do is, basically, you've got 4 colors. We've got yellow, very yellowy green, light green, and dark green. And so every pixel in this image is assigned its closest match of one of these colors. So every pixel has to make a call. Are you going to go with yellow, green, light green or dark green? And that's it. And so the subtle gradient that we had there is now completely gone. And it's just boom, 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 1, 2, 3, or 4. But with just 4 colors, we need only 2 bits per pixel. So if you were to look at what this image looked like, this pixel here would just be 0, 0, then 0, 0, 0, 0, 0, 0, all over 0, 0, and then maybe go to 0, 1, 0, 1, 0, 1, 0, 1. By the time we get here, we'd have 1, 0, 1, 0, and then onto a new row. So here we could represent each pixel with only 2 bits, because there's only 4 different colors in this image. Now, of course, knowing that there are only 4 colors doesn't tell you what colors they are. I mean, in the RGB system, if I told you the color was 255, 0, 0, it's more than color number 15,092,092. You know from looking at the values that it's red. However, in this scheme here, we've got color 1, color 2, color 3, and color 4. There's nothing about that information that tells us what colors they actually are. And so in a scheme like this, which we call indexed color, we have to use a color lookup table to tell us what the colors actually are. So although we do save loads because we're only using 2 bits per pixel, we do have to actually have the overhead of the color lookup table, which will tell us that color 00 has this RGB value, color 01 has this RGB value, color 10 has this RGB value, and color 11 has this RGB value. So it's a bit like paint by numbers, where each pixel in the image is given a color. Might be color number 1, color number 2, color number 3, color number 4. And then you have to go and actually look up what color that would be. And so we call this indexed color. And each pixel is just stored as the index into the color lookup table. So GIF does something like this. Now the color lookup table is also known as a palette. So you'll often hear graphic designers, well actually sometimes when they talk about palette they mean something different as well. But in the context of indexed color, the palette is the lookup table. So let's say I have an image that's stored at 24 bits per pixel. So I have the possibility of 16 million and something colors. Now, if I wanted to save that at, like GIF for example only has 256 possible colors. If I wanted to save that with just 256 colors, well then I would have to choose which 256 colors. Now, if it turned out that I was lucky enough that the image only had 250 colors in it anyway, if there was only 250 different kinds of pixel, Well, then that would be a trivial problem because each pixel color could get an entry in the lookup table. So color number 1 is whatever, color number 2 is whatever, color number 3 is whatever. But the problem is if you have more than 256, then it has to go to the closest match. And so that can cause problems. But one of the things that Photoshop can do is it can look at an image and say, well, based on what's in this image, this set of 256 colors is what you should go with. And looking at this image here, you could see how this color palette here goes with this image. So the palette is based on the images in the color. Sorry, the colors in the image. If we look here, this image is different. The formatting of the text now is screwed up here. But in this image, the colors are different. And so when you choose the best 256 colors with which to code this image, you get a different 256. So here's 256 colors, which would be, these would be good pots with which to paint by numbers this picture. If doing a paint by numbers of this picture, these 256 pots of color would be best. Similarly, this image here has a very limited range of colors, and so the best 256 colors with which to represent this image are here. So there'd be no blues in the palette for this image. That would be a waste of a slot. So let's have a look at these images here. So here we have an image and 3 palettes. This is an easy one. So which palette here is the palette that's best for this image? Obviously the middle one there, because there's no color in this image. So in this image, you need 256, you've only got 256 slots. What should you fill them with? Well, you fill them with shades of grey. Actually, as I suspected with this image, it doesn't even have 256 shades of grey in it. So that's why there's empty space there in this palette, in this lookup table. What about this image here? By the way, if ever you wake up with a hangover and you can see both the Eiffel Tower and the Statue of Liberty, you're probably in Las Vegas. But you could be in Paris, as it happens. The French made a small copy of the Eiffel Tower, of the Statue of Liberty before they sent it to New York. So which of these palettes is the one? It's tougher, isn't it? I think clearly this sandy colored set here, you know, is not the one. So it could be this one or this one. I think this one has maybe a bit too much green in it for my liking, but it's a close call.
Not really enough red.
There's not enough of a lot of things, really. This image is more colourful than I think this palette would do well. So I suspect it's the top one, but it's close, isn't it? Yeah, and it's that one there. How about here?
The middle one really for the blue and the green.
I think so. I think there's so much blue in this that it really needs to be this one. There's so much blue and so much green. I mean, these doors here, you know, are a bit brown, but you could see those browns are accounted for there. I think the top one definitely not. It's too autumnal.
Because you've probably got like 50% blue in it when you look at the water on the sky.
You know. So I think it's clearly the middle one. This one here. I think it's safe to rule out the bottom one, can't we? There's just too much blue in there. We don't have the reds and the pinks in here that we need. We might get away with the greens, but I'm not sure.
Probably the top one, because dark.
Yeah.
The middle
Yeah.
bit's really dark.
Yeah. And also the top palette has got more stronger colors. In fact, when we talked about hue, hue, saturation, and brightness, if you look at this image, the colors are quite saturated, aren't they? And if you look at these palettes here, this is the palette with the really saturated colors. I would say it's the top one. And sure enough, it is. And so what Photoshop has done here is took an image with possibly 16 million different shades of pixel. And you said, look, we're going down to 256. So we're going to do like an indexed color, a paint by numbers scenario where you have color number 1, color number 2, color number 3, color number 4. Give me the best choice of 256. You pick the 256 for me. And it does a whole bunch of math to figure out what's the way to go. Here.
Definitely not the green.
Definitely not the green one anyway.
I'd say the top one on there, because there's not really that much blue.
Yeah, I think there's too much blue in the bottom one there. If the sky was blue here, maybe I might go for the bottom one, but I think this isn't as colourful as this cow needs to be rendered well. Here, the bottom one is too blue anyway, isn't it? Yeah. And I think the top one has too much green that isn't in use. So I think this is an easy one. Okay, here's a palette. Which image is it for? I think we can rule out the New Orleans cable car anyway.
And the top left, because there's no blue on the top left.
Yeah. Interestingly, actually, this is hard. And I think it's no coincidence. These are all from the same city, actually. I wonder, could you do some science where, if you're just looking at the palette of an image, could you have a guess, which of 5 cities it might be from? I mean, this is from San Francisco. On perhaps the same day, on a brighter day, you might have got a different palette. Certainly, if you went around town today taking pictures, you could probably use the same palette for everything. I think the top left one, anyway, we can maybe discount. It doesn't have need for that blue. And then it's really just a question: is it the bottom of the CMYK building or the top of it?
So the bottom left, because there's more brown in the bottom left than there is in the top.
Yeah. I mean, there's a lot of brown, kind of reddish here too, but it's not so much.
Color images,
yeah.
More brown in the bottom left.
We'll see. Okay, it turned out to be the bottom one, but it was certainly close. Here. Which of these might it be? Or which can we discount, perhaps? Now, interestingly, what's happened here is, in this case, I've said to Photoshop, I'm not looking for 256 colors. I think I went for, that looks maybe like 128, which is a lot less. So you don't always have to have 256. I think we can rule out this one anyway. There's no need for green there. There's no green there. This is certainly a lot of colors, but I think this palette would need more reds and browns to do this well. I think we can rule out the car, which is from Havana. Interestingly, I think it's down to these two, and as it happens, these were both from the same city on the same day. This could be Ireland. It's not, but it could be. So I think it's between either the top left or the top right. I think the top right doesn't need the blues and the whites so much, so maybe it's the top left. But it could easily be the top right. Turned out to be the top left. Ireland, Which one? Ordinarily, you know, your 40 shades of green would be a good bet for Ireland, but we have this thatched roof here, and let's face it, it wasn't a very grassy area. Could be the top, could be the bottom. I would go for the bottom myself. I just think it just reflects the sky and the doors a bit better. Yeah, it was the bottom one. Okay, so we'll leave it there. So the point here is that you are reducing the number of colors in the image to say 256 or 128. You do have to do some work to figure out which ones you should go for. But thankfully, Photoshop does that for you.